All right, my friends, let's see how it went here. I'm going to go ahead and grab part D here. I'm going to start with that one. So I wonder what you said. If the limit as n goes to infinity of a sub n plus 1 over a sub n equals 2. So let's take a look at this. What would that mean? That would mean as n approaches infinity, remember n means the number of terms you're on. So we're talking about at the tail end of this thing, if you're to graph it, we're talking about the far right of the graph. If the absolute value of a sub n plus 1 over a sub n, if that's 2, first of all, I hope it makes sense that that would mean the part inside the absolute value marks could have been either positive or negative 2. And then if you were from there to clear the fraction, it would say a sub n plus 1 would be plus or minus 2 times a sub n. And so that's why I had to do that first warm-up to kind of digest what something like this would be saying. So something like this is saying that your sequence basically starts acting like a geometric with a common ratio of either plus or minus 2. So I hope it makes sense that if as n approaches infinity, if at the tail end your terms are basically getting doubled in magnitude, that the sum would definitely diverge. And so we would say the sum as n goes from 1 or whatever to infinity of a sub n in this case would diverge. I hope that makes sense. Now, before we move on, I do want to make sure you're okay with the theory that we're going to use here. This notation we're using is very, very ratio test-esque. So basically what we're finding out with all of these different statements, notice they kind of have similar patterns, is basically like at the tail end, we're finding out that even if a sequence wasn't geometric at first, maybe it was all sorts of crazy things, maybe the terms of your sequence kind of look like this. What we're finding out is if you get a constant value from an expression that looks like this, if you get a constant value of any kind, we're basically finding out that while it may not have been geometric at the beginning, but at the tail end, it starts acting like a geometric. And we can tell, whether it would converge or diverge based on what kind of common ratio do you have. And so for part D here, you would have either had a common ratio of 2 or negative 2. And we already know from previous work that would mean that the sum would diverge. And so there you go. And if this thing, I hope it makes sense that really what makes or breaks a series for convergence or divergence is what happens as n goes to infinity. Is like when n is finite, nobody really cares because a finite number of finite numbers is finite. Really what matters is way out here as n approaches infinity. So now let's look at, now let's do the next easiest one, which I would say is part B probably, maybe, I don't know. So for part B, we'd be finding out that as n approaches infinity, the absolute value of a sub n plus 1 over a sub n is 1/2, which would mean that part inside the absolute value marks could have either been positive or negative 1/2. And so that would mean that to get any term, as n goes to infinity anyway, you basically multiply the previous term by plus or minus 1/2. So for part B, at the tail end of the series, you have it starting to act like a geometric with a common ratio of either plus or minus 1/2. And so, what do those do? Well, they certainly go to 0 fast enough. And so we would say in this case, the sum as n goes from 1 to infinity of a sub n, that converges. How come? Because at the tail end, as n goes to infinity, it starts acting like a geometric with a common ratio of plus or minus 1/2. There you go. Let's do part A. That one's the next easiest. So as n approaches infinity, I'm going to skip a couple steps that I've been showing. Basically, we'd find out that a sub n plus 1 is equal to 0 times a sub n, which would mean that as n approaches infinity, the terms basically are 0. And so I'm hoping that you went with that the sum would converge here. So now if you were just guessing and you were like, great, that's what I guessed, then great. But I'm hoping that my logic is making sense here because it'll matter in just a second. Here. Okay. Now for part C is kind of interesting. So let's think this one through. So as n approaches infinity for part C, we'd be finding that a sub n plus 1 would equal plus or minus 1 times a sub n. Now this one we'll find that it could go either way, because what we're finding is that, let's play around with the positive one first for a second. Let's say you have a positive one here. What we're finding out then is that as n goes to infinity, as n goes to infinity, we're finding out that this thing flatlines. Like the next term is the same as the one in front of it. And so it would depend on, as soon as it starts behaving this way, how close to zero were you? If you were already so close to zero that your terms were going to zero fast enough before it flatlined, then it would converge. But if your terms flatlined but they were still a little too far away from zero, then you would end up with something that diverges. And so part C is the one with no guarantee, as in it could have gone either way. And so we'll just say, we don't know. It could converge or diverge if it flatlines at the end. So, okay, so now that we've had that discussion, let's introduce the ratio test. And my friends, the ratio test, I think of it as kind of like the big stick of tests for convergence and divergence, as in the ratio test works on most things pretty well. It's a little more work, but once you get used to it, it goes really fast, okay? Now remember, if we leave bounds off of the sum, it means that it's an infinite sum. It starts at some lower bound and it goes to infinity. So if there's no bounds, it means an infinite sum. So let the infinite sum of all the a sub n's be a series. And the only condition for using the ratio test is that you've got a series of non-zero terms. And so if you do, then actually, let me write this differently. I apologize. Let's see. And I hope you are copying this part because this is definitely a main idea. We would say that the sum of all the a sub n's converges. And it doesn't just converge, it converges absolutely. Remember, that means that it converges as is. And if you threw absolute value marks on all the terms, it would still converge. So it's the strongest type of convergence. So it converges absolutely if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And then what I want you to do is see if you can fill in the rest. So what kind of numbers can we get for this expression and find out that the sum converges absolutely? Oh my goodness, sorry, it keeps moving around. Anyway, so I think I'm going to leave it there. There's more to the ratio test, but I'm going to see if you can fill this in with something that makes sense, and then we'll check in the next video and see if you got it. Good luck.